Alright, let's continue. Okay, let me open the table of content first. Okay, where is it? We are still in chapter 28 here, logs, and still on homework simulation section. Let me open that. Okay, previously we take a look at the Peterson algorithm here, right, until question 10. Now let's take a look at question 11, ticket.s. Okay, what is it? Trade logs, I guess. Okay, trade log ticket. Okay. Now study the code for ticket log in ticket.s. Does it match the code in the chapter? Then run with the following flag. Okay, causing each thread to loop through the critical section 1000 times. What happened? Do the thread spend much time spinning for the log? Okay, let me check. Ticket log. This one. Okay, we have struck here. Okay, init. Alright. Check the turn here. Fetch and add. I assume this one. Fetch and add is adding, okay. Adding the old value or maybe the old ticket number by 1 and then returning the old ticket number, maybe something like that. Okay, not equal my turn, then we spin until it is our turn, and then to unlock that we change the value in turn by adding 1 to it. Okay, now let me check this. Grab a ticket. Okay, I'm assuming the ticket for the current thread is in this ticket variable. And then check if it is our turn. Where is X? Okay, where is it? Okay, so we change the, what is it called? PX register value instead of CX. Okay, I'm assuming the default value in CX is 0, maybe something like that. X fetch and add. Let me check. Fetch add. Okay. are we gonna add the value in this register with the current ticket, maybe something like that. But yeah, why there are two register here? I assume this is the value for the current ticket. This might be the value in this register, but I'm not sure what the register value is. Yeah, like, what is this? We have to argument, right? Source destination and destination split. Wait a minute. Oh, maybe this one. No, maybe not that one. Yeah, maybe direct memory. Something like that. This is label. Okay. Oh, there is 1, 2, 3, 4 for return value. I assume this is the variable value. This is register translate 0. What is this? It's not a valid register. Self-register. Okay. I am not really sure about this. Maybe hidden zero value register. Okay, maybe we have this zero register to save the value for variable. Maybe something like that. But why do we have two here? That is interesting. And then the last one is returning 1. Okay. Oh, if that is the case, temp 0, temp 1, temp 2. 0, 1, 2, okay. I assume this is the temp 0, temp 1, temp 2. Maybe something like that. So this one, the value in the variable, maybe something like that. And this is the register 0. Maybe. what do we get here? Are we adding 0? Maybe. Okay. Register source. This one, okay. Okay, so we get the value, right, from the ticket log here. Here is it, or from the fetch and add here. Then something like this, right? Get the old value in this one, and then we add that. With this one, I guess. The content in the source register, something like that. And then we replace the content in the source register with old value. Okay, and then we put this addition into the memory, something like that. So I assume this register now contains the register now contains the old ticket value. It is probably 0. Probably 0. First run x equals 0 maybe, and the ticket here probably something like this. I mean, we didn't provide, what is it called? Yeah, we only provide register. Oh, not register. What is it? Wait, yeah, this is the register. Register px value. Okay. And then the ticket probably also 0. Because if I understand correctly, the ticket initial value is also 0. And oh, wait a minute. The ticket initial value is 0, but the register initial value is 1 because of this. So the ticket should be 1. Because in this case, right, we are doing something like this. 0 plus 1. 0 is the memory in the variable on the first run, and then the value in the register AX here is actually 1, right? Because we specified that in this instruction. So this one should be 1, this one 0, and then the result, I assume something like this for the first run, at least first run on the first thread, maybe something like that. Okay. Okay, check if it is our turn. And again, I assume the value in this one, in this variable, is 0. The initial value, maybe something like that. And then we check that. In this case, it looks like 0 equals 0, something like that. And then if not equal, we check again, right? This one, the iteration in this one, the spinning weight. Okay, and then if it is the same, in this case I assume it is the same, we enter critical section, then release the lock, fetch add again by what is it called, adding 1 to turn. So ax equal 1 because the previous ticket value is 1, and then the ticket equal to. So we return the old value or previous ticket number in register ax and increment. Oh, wait a minute. Okay, looks like we are doing this one. We increment the turn, not the ticket. Okay, turn, I think equal 1, 2, and the ax, in this case the ax would be 0, right? Because the previous turn is 0, 2, the ax 0, and then turn become 1 because of this. Oh, yeah. Because of this, that means turn will be like 0 plus 1. Maybe something like this. And this one is the old turn value. Maybe something like this. See if we are still looping. Okay. Yeah, this is the, what is it called? The register value that we change. Instead of using 0, we are using 1000 here. 1000 times. Okay, I assume we are using the, what is it called? The default value for auto flag, like maybe interrupt here every 50 instruction, and then the thread. I assume we also use the default value here, which means 2 thread instead of 1. Okay, let's try that. But before trying that 1000 times, maybe let's try 5 times first. Maybe. Thread logs, okay. Where is set ticket. Okay, and then okay, ticket, and then the initial value here for the register px. Okay, 5. If I remember correctly, if we provide 1 initialization like this, we will use the same initialization value for all the thread, if I remember correctly. Take the memory here, probability get, and then turn. Should I check the count too? Maybe. And then register trace here. The register. What register do I want to trace? Maybe AX. I want to trace CX2. I mean, we already trace turn, right? Maybe not. Maybe AX and PX for the iteration. Maybe let's try this. Okay, we are entering the, what is it, critical section on thread 0. Okay, and then I guess we release the lock. This one. Check the iteration again. Okay. Alright. Oh, okay. Maybe the header every 5 instruction. Okay. Try again. Okay. To be x, reduce to 4, and then 3. Okay. Okay. Until 1. Oh. Okay, I assume we haven't finished the 0 computation, but there is an interrupt here, so we are moving to thread 1, going through the same until we got the, okay, until the last index, I guess, greater than, right, greater than 1, so the last index should be, yeah, we are doing another iteration here. Should be execute too, not immediately going to halt here. So we are going back to the top here, this one. Okay, my turn. Check again, and then we are halt. Okay, alright. Now the book here wants us to try 1000 times. What happens? Do the threads spend much time spinning waiting for the lock? Can we check? Maybe 100 first? I'm not sure if we really need 1000 to check the behavior. So let's find out. Okay. Let me check. That's okay. What? Oh, okay. 96 and then interrupt, right? I think it's gonna be the same here. Okay, 26. Okay, another interrupt. Okay, yeah, looks like a lot of iteration. Do the thread spend much time spinning for the lock? Spinning for the lock. Maybe not. Oh, wait a minute. Wait a minute. Hold on. Try again. So maybe the thread is spinning, waiting for the lock. Okay, at least I assume we go into the critical section on that 0 here. Okay. Alright, next ticket, okay. Entering the critical section again. Okay. I think this first run is fine. Not necessarily the first line. Before the interrupt, I guess it is as expected. Maybe something like that. after the interrupt. Okay. This. Okay, try again. Okay, we enter critical section here too. Okay. And okay. Try again. Okay, we are still entering the critical section. So stuck. Oh, okay. Going back to the top here. So I'm entering the critical section here. Oh, wait a minute. If this one start from ticket 8, that's 0, ticket 0 until, what is it? Ticket 0 until ticket 4, maybe something like that. Interrupt. Something like this. Ticket 4. Until ticket 8, I guess. Fetch at AX. Okay. Oh, wait a minute. This is the previous ticket, right? So maybe until 3, and then that one ticket 4 until ticket 7, maybe something like that. And then interrupt again. Thread 0. X is 3. The AX in here is 3. Okay, move 1. 8. Okay. Ticket 8. Move turn. Okay. Until probably something like that. Wait a minute. Yeah, maybe 11 because of fetch add in this case. Move on to AX. And then interrupt. That one. I some ticket 12. Maybe. Fetch add. Okay, this. This one. Going back to this one. Get 12. Turn. Okay. Oh. Wait a minute. Fetch add turn, right? And then check and then try again. Check if it is your turn. Oh. Yeah, this is the interesting part, I guess. Because we have interrupt. What is it called? Because we have interrupt before we release the log on thread 0. Before release on thread 0. The thread 1 in here keep spinning, waiting for the turn. It is never gonna change. Because again, we are in this section, right? We keep spinning in this section. See, the turn still equal to 11. Meanwhile, previously, the turn on thread 1, right, increasing. 4, 5, 6, and so on. But after this interrupt, and we change to thread 1, we cannot increment the turn. So the thread 1 will keep spinning in this section, try again, until another interrupt happen. Another interrupt happen, and then we are going to the thread 0 again. Yeah, that's why I feel like, are we repeating this over and over again? And it looks like we are. I found some pattern, maybe something like that. This one, try again, right? And then try again. After the interrupt, what is it called? We increment the turn at some point. Where is it? Oh, okay. This is another interesting part, I guess. Ticket 12 in thread 1, and then interrupt here. Thread 0, right? I assume because ticket 12 is in thread 1, so when we increment the turn in thread 0, we cannot continue again in the thread 0 because thread 0 got ticket 13. Okay, let me check first. If it's add, we increment the turn, right? The turn finally changed from 11 to 12 here, and then iterate again, going back to the top. It is this one, right? And then fetch add for the ticket. Let's add for the ticket. The last ticket number is 13, right? So we take that and then increment it by 1. So thread 0 have ticket 13. Per turn is for ticket 12. It is on thread 1. If I understand correctly. So thread 0, right, is spinning again. The same way that thread 1 spinning. Yeah, test, right? If not equal, try again. Move to register, test again, try again. This is the full instruction, maybe something like that. Or full section, I mean. Right. Move turn, CX, test, CX, AX, GNA, try again. Jump if not equal, try again. So thread 0 also spinning, keep spinning until interrupt 2. Because the current ticket turn is not in the current thread, but in another thread. So maybe we're doing that quite a few times here. Yeah, maybe. See, even in the 100 ticket, right? We got ticket 195, but the current ticket turn is 194, which is on thread 1, I assume. Now we continue in the thread 1. Okay, yeah, this one maybe. Increment the turn. It is on ticket 195. and ticket 195 is on thread 0. So thread 1 keeps spinning, because the turn is for ticket 11. So keep spinning until another interrupt. Maybe something like this. So that is the interesting part about this ticket lock, I guess. If the interrupt happen at the right timing before the release, another thread might need to keep spinning until another interrupt. So there is that. Do the threads spend much time waiting for the lock? Yes, as far as I understand. How does the code behave as you add more thread? I'm assuming this one, right? The ticket lock. Probably gonna take more spinning, I guess. I mean, it depends on the interrupt, right? If the interrupt happening right before the release of the lock, then as we increase the thread, then the time waiting in this another thread, no, not like that. The time we wait is gonna keep increasing because we have more thread spinning. Like for example, in this case, we only switch between thread 0 and thread 1. Now imagine if we also have thread 2 and thread 3. So thread, let's say thread 1 spinning, and then there is also thread 2 spinning again, and then thread 3 also spinning, and don't forget the ticketing will keep increasing, right? So the time waiting for the lock, if the interrupt happen before the current thread release the lock, is gonna keep increasing too. I assume something like that. Okay, now examine yield, in which a yield instruction enables one thread to yield control of the CPU. Now examine yield, in which a yield instruction enables one thread to yield control of the CPU. Realistically, this would be an operating system primitive, but for the simplicity, we assume an instruction does the task. A yield instruction enables one thread to yield control of the CPU. Okay, realistically this would, okay, operating system primitive, but for the simplicity, we assume an instruction does the task. Find a scenario where test and set recycle spinning but yield. Okay, but yield does not. Oh, okay. How many instructions are saved in what scenario to this saving arise? How many instructions are saved in what scenario to this saving? Okay. Oh, hello, Headstone. Welcome. Ticket mode text after barriers. Ticket mode text are my favorite multi-threading structure. Oh, okay. I'm kind of curious why ticket mode text is your favorite structure, I guess. I mean, again, I'm still new, so I'm not really sure. What is the benefit and disadvantage of this algorithm? Maybe something like that. Okay, my follow-up question to question 12 that I would ask if you were my student. Is it possible for one thread to never get a chance to take the lock? Is it possible for one thread to never get a chance to take the lock? For one thread? I assume what is it called? Maybe there's a possibility that one thread never get a chance to take the lock, but yeah, I'm not really sure how to reproduce that, yeah, like how do we check if what is it called? By adding more thread, there is a possibility that one thread never get the chance to get the lock, maybe something like that. In my, what is it called? In my mind, probably there is a chance that one thread did not or never get the lock, but I'm not sure how to reproduce that. Yeah, like for example with this, what is it called? With this simulator, what kind of option should we use to reproduce that? That will be interesting to try out. Maybe let's try this out and see if I can reproduce that or not. Okay, let's use 100 iteration, and then what option should we use? Maybe rather than using the constant interrupt frequency here, maybe we can try a specific thread schedule, something like that. Control exactly which thread run when, and of course increasing the thread, maybe to three thread, something like that. Control exactly which thread run when. Yeah, maybe if it is your turn, if we only have 3 thread, never get the change. I mean, if we're gonna increasing the turn, right, every interrupt, hello my cat, welcome. Do you have any higher education? What do you mean higher education? Higher than what? Okay. My turn. If it is your turn. If we increase the turn, right? 0, okay, and then 1. Let me try imagining that. Okay, let's say 0 and then change to 1 before release. And then increment by 1, increment not turn but ticket, right? And then on thread 2, if on maybe to answer headstone question, is it possible for one thread to never get a chance to take the lock? Now that I think about it, maybe not. Yeah, maybe. I mean, we are gonna keep increasing the ticket, right? Oh, where is it? Not that one, but maybe this one. We're gonna increasing the ticket, right? And get ticket for the current thread, maybe something like that. Okay, let me type this. Is it possible for one thread if we increase, I think, add more thread. if we increase the thread with ticket locks mechanism, not that one. Is it possible for one thread to never get the chance to get the lock, to take the lock, for one thread to never get the chance to take the lock. Yeah. Probably not. Probably no, because by that time the ticket locks mechanism enter the thread, it will assign the ticket for its thread and it will assign the ticket for its thread and make sure that each thread have its turn at the cost of another thread spinning. Question mark. I'm not sure if this is correct or not. Correct, as long as the threads are running on a fair scheduler, every thread will be able to take the lock. No thread will be stuck and unable to get the lock. Oh, okay. Any real operating system will have a scheduler that is fair enough for this purpose. And to answer your earlier question, that's why I like ticket mutex. They kind of fall into this space where they are simple enough to understand easily, but useful enough to use in real life. Oh, okay. Alright, I'm still not sure the use case in real life with this ticket lock, but I will keep that in mind. I mean, again, it is simple enough, I guess, to understand, but at the same time, it also makes sure that all the threads have chains to get the lock, so no thread stuff, something like that. That is quite nice, okay. But yeah, the keep spinning is maybe kind of interesting, right? And maybe that's why there is this yield mechanism. So instead of keep spinning, we yield control of the CPU. Maybe we take a look briefly. Yeah, this one. Just yield, baby. Okay. Thus, anytime a thread gets caught spinning in a situation like this, it wastes an entire time slice doing nothing but checking a value that isn't going to change. The problem gets worse with n threads contending for a lock. Okay, n negative 1 time slice may be waste in a similar manner, simply spinning and waiting for a single thread to release the lock. And thus our next problem, right? How to avoid spinning. How can we develop a lock that doesn't needlessly waste time spinning on the CPU? Okay. So maybe this is why we are talking about yielding the CPU rather than keep spinning, I guess. Okay. I try to take down a real life use case for ticket mode text. I know of a video of someone talking about and actually using them. Oh, I'll drop it in the Discord when I find it. Oh, alright, thank you, Headstone. Yeah, I'm just curious, I guess. If you cannot find the video, then it's okay. Maybe one day I will know how to use this ticket lock or ticket mode text. Okay, lock with test and yield. Okay, I guess let's continue this on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.